Sweet. G'day. I'm Nicholas. I'm here to do a revision seminar for Maths 1B, second semester 2025. It's the last one I'll ever do because there is no 1B in the new university. I'm like, whoa. Trust me, from 25 years ago, I thought this day would never come. No, actually, 25 years ago, I was worried about when the day would come. Now, not worried. It's a revision seminar. So that means you guys ask me questions. If you don't ask me questions, someone wrote something on the piece of paper. And so I will go over the things on the piece of paper and do those. And if you want to sort of, be quiet and sort of stuff. As I've said to some of the people who arrive early, I make mistakes on a very regular basis. If you see me doing something stupid, please tell me so that I can fix it. All right, hey, I did -5 and it turned out I did +5. But, like -5. And I'm like, no, that's not right. So I like to know when the things that, the words, the thing I think I'm doing and the thing that actually I did don't match. That makes my life easier. Also makes your life better because this makes it actually correct. And correct mathematics is there's people get uptight about it, really. I think a little bit too much emphasis is placed on getting maths right. So the other thing to talk about is when I switch to the document camera that I have here, my computer is lagging like there's no tomorrow. So I'm not seeing this. All right, sweet. See if we do that. All right, about 4 seconds delay. Sure. So unfortunately, the screen and what's actually happening have got about a 4-second delay on them, which will suck ass. All right, but I don't know what's wrong and don't know why it's decided to be so bad. So, but anyway, there is so because this is being recorded, the recording will go up on the Math Learning Centre's website. Oh, come on. Right, beautiful. We are doing that. So we'll go up on the website. That will happen today or tomorrow. David takes care of that because David takes care of everything. I will just So, but really, got questions, ask questions. I spent what, about somewhere between 10 and 15 years working for the School of Maths. So I have done a lot of this stuff. I did a lot of exam marking when I was with the School of Maths. And so I know most of what's going on. I know the sort of things that appear in exams, but there may be something you want to ask specifically about. And so please just ask. All right. So do we have anything you want me to start with, or shall I just go on with the first couple of things? Because the things that were on the sheet were mostly about directional derivatives, multivariable functions, stuff. So what I did is I looked up a book and thought, oh, I haven't done a problem like that before. No, I've done a problem like all of that, but it's not pick something that is sufficiently simple. So one of the things to remember with exam type questions is that we want you to demonstrate understanding of the material. We don't want you to do complicated calculations. All right. Sometimes if you're doing a complicated calculation, ask yourself, did we want you to do that or have you missed the point? All right. This can be a thing, right? Because a lot of the maths exam stuff isn't about being complicated. It's about demonstrating a point. I haven't actually done the working on this. There's about half a dozen pages on my desk of me trying different examples and see what works. And I haven't actually tried these ones, but I tried some examples that I was like, oh no, that's terrible. I don't want to do that. So we'll give it a go, see how it goes. If it goes terribly, I'm going to blame someone else. I'll blame David. It'll be fine. Why are you not doing that? Why are you not going away? All right. So what we're going to do is we're going to start with our z, which is equal to 3x cubed y to the 4 minus x squared on y squared. All right. So firstly, what we should do, I feel like, we could do a gradient vector. So we could do like, so we're going to, another way to do this is to call this f of xy and just say z is equal to f of xy. One of the things they actually do in the course is f of xy minus z is equal to 0. It's same, but ever so slightly different, okay? Ever so slightly different. And it's going to help us when we come to working out things. One of the first questions you'll get, like if you get this sort of thing, one of the things they might do to start with is like, they might say, verify this point is on the surface. This is not a trick, people. You just plug the numbers in. You go f, well, x is 1 and y is 1, so f of 1, 1. And so that's going to be like 3 times 1 cubed times 1, 1 to the power 4. See this? Minus 1 squared on 1 squared, which is going to be 3 minus 1, which is equal to 2. That's my z value, so that's a tick. That is all you have to do. It's worth 1 mark. Going, hey, I understand how multivariable functions work. All right. So sometimes they'll go, hey, we'll put in something so that you can just do these things. All right. Find grad of f. All right. This is the vector, partial derivative of f with respect to x and partial derivative of f with respect to y. All right. So partial derivatives. So when I do the partial derivative with respect to x, I say to myself, holding all other variables constant. So I'm treating x as the variable, but I'm holding all other variables constant. So partial derivative of f with respect to x is going to be, so because this first part, I'm treating y as a constant, this is just like 3y to the 4 times x cubed. And the 3y to the 4 part is a constant. So 3y to the 4, derivative of 3x x cubed is 3x squared. Nice and easy. Ba-dum-ching. All right. Same with the second term. All right. The x squared on y squared. So the on y squared is like a constant. And so I can times by the derivative of x. All right. Possibly I would simplify that down to like 9x squared y to the 4 minus 2x on y squared. All right, sweet. Let's just go through the same process with the partial derivative with respect to y. Okay. With respect to y, we're going to go 3x cubed times by 4y cubed. And then minus x squared times by derivative of 1 on y squared, or y to the minus 2, is going to be minus 2 times y to the minus 3. All right, sweet. So we're going to simplify this down again. So we're going to have like 12x cubed y cubed, and then plus 2x squared on y cubed. Sweet. And so my gradient vector is going to be equal to 9x squared y to the 4 minus 2x on y squared, 12x cubed y to the y cubed plus 2x squared y cubed. Sweet. Okay. It's a vector. All right. So, favorite thing to ask. Which direction is the function increasing most rapidly? All right. Anyone want to guess? All right. The answer to which direction the function is increasing most rapidly is the direction of the grad. Yeah, beautiful. Yes. Yeah, that's what you were trying to say? All right. Hashtag for those people in the audience, I'm quite deaf. And so if you're going to say stuff, kind of yell at me. I don't mind it. So if I do grad of f evaluated at 1, 1, and 2, that is going to be equal to 9 times 1 times 1 minus 2 times 1 on 1 and 12 times 1 times 1. There should be like a 2 and a 4 here and a 3 and a 3 here and a squared there and a plus 2 times 1 on. We should simplify this down into a single number. This would be 9 minus 2, so that's going to be 7. This is 12 plus 2, so 14. Hey, check that out. So in a two-dimensional sense, so this Z describes, we could think of this Z as describing the height. We need to push, no, we don't, a little bit. We could think about this as describing the height above the plane, and this direction, sort of 7, 14, describes the direction in which this function is increasing most rapidly. Okay? So, and you're kind of going, oh, okay, so more in the y, that kind of makes sense because it's the y to the 4. And away from 0, that's going to be the dominant term. So once you're past the little bit that sort of where x and y are less, the absolute value of x and y are both less than 1. So this term, this second bit where we're taking off this x squared on y squared, that's probably going to dominate near 0. Probably should have pointed out that this is not defined for y is equal to 0. Oh, domain. Hadn't thought about that. Right. A thing they can get you to do, which this function does nicely, is talking about the domain. I'm going to just sort of, whenever we talk about domain, so all right. The way I describe talking about the domain is what restricts the domain. So, and in this case, this bit here is basically like the first part, the 3x squared x cubed y 4, kind of polynomial like. So we don't need to worry about it. All right. But the divided, so the x squared on y squared, so the denominator must not be 0. So that's the thing that's going to tell me what's going to happen. All right. And so I'm going, okay, well, I can be fairly confident that, so my domain of f so all x and y in R2 such that y not equal to 0. All right. So I'm just excluding the x-axis where y is equal to 0. All right. for the fun of it. Oh, there could be a thing. Maybe we'll have a think about that in a second. What's so we've got our point, we've got our directional derivative. All right. So maybe I could work out the equation of a tangent plane for this thing. Yeah. All right. What do I need to find an equation of a plane? The normal vector. Sound like a great plan. And the normal vector in this case is going to be so partial of f with respect to x, partial of f with respect to y, minus 1. Hang on, minus 1? What the hell? Why did we say minus 1? So we're going to pull this page down a little bit and point out one of the first things I wrote about this thing. Wait for the system to catch up. Because we've written the function this way, all right? So normally a surface is three-dimensional function equal to a constant. This is function of three variables equal to a constant, and the partial with respect to z is minus 1. Strictly speaking, if I put minuses here and made this plus 1, I could do this, I could do that as well, right? But that is just the normal, like a scalar multiple of the normal. All right, so we have our point. We have a vector, we have a point that's on the plane. So we know, so I like the version of the plane which we go normal dot with x, y, z is equal to normal dot with p. Some people will tell you normal dot with x minus x naught equal to 0. All right. They are equivalent forms. All right. And I like this because I remember it. Basically, when it comes down to what makes a formula good, being able to remember it makes it good. Okay. So I've already worked out my values. So this is a tangent plane, and then we should say at 1, 1, 2. We've verified that this point is on the surface. So we're going to go, hey, this is the thing. My normal vector, I'm going to write as a row vector, 14 minus 1. Well done. X, Y, Z is equal to 7, 14 minus 1, and 1, 1, 2. Oh, hey, that would be weird. Okay, sure. So this is going to be like 7x plus 14y minus z is equal to 7 plus 14 minus 2. That bit's equal to 19. Sweet. So my tangent plane all right, tangent plane's not terribly informative. You can kind of go, okay, it's a tangent plane, people. We're excited. Um, a bit like a straight line, you could use it to give yourself an idea if you wanted to visualize it. I'm not even going to try. I humbly recommend taking something. You can make MATLAB draw you graphs. There's any number of other things that where you can enter a plane. You could enter this function into like Wolfram Alpha and it will give you a bit of a sketch of it. It's kind of like you don't even have to think. It's like no thought process. All right. So I haven't actually, again, haven't done that because I was like, oh, let's do that. And then I thought it'd be more fun if I make it up as I go along. Okay, So we've got my tangent plane. What else was on my list? All right, we've got the normal vector. We know the normal vector. Okay, that's the sort of, hashtag things like which is the direction of the greatest increase is also equivalent to asking which is the direction of the greatest or the greatest decrease and you just put a minus sign in front of the grad vector. Not that hard. Nobody ever does what direction would the isocline level curve be? What would be the slope of the level curve at this point? All right, because slope of the level curve is going to be perpendicular to the direction of greatest increase, because it works that way. You think about it, if that's the direction of greatest increase, that direction there is no change. Maybe we should work out level curves. What would we do if we're trying to work out level curves? I'm not sure if this is going to be terribly interesting. I come up with these ideas and I go, let's give it a go. So I had f of xy is equal to, what did I say? 3x cubed y to the 4 minus x squared on y squared. All right, I'll give it a go. So this really simple, all right? We may not be able to say anything very interesting at all right? Because what we're going to do is we're just going to go, this is what the z value is. We're going to go 3x cubed y to the 4 minus x squared y squared is equal to 2. That's all we're doing, all right? And the worst part about this is there's not an easy thing I can do, right? This one is not going to lend itself nicely. It's not going to lend itself nicely to sort of splitting up into sort of X's and Y's. There is just nothing fun about this one. So we can't really say much about it. This is where you go, maybe. Okay, local extrema. What do we reckon? I have my feelings. All right. I'm going to exclude where the thing is not defined because that makes sense. All right. Okay. So we should have our partial derivatives equal. So we should go fx, xy equal to 0 and fy, xy equal to 0. I may abandon this because it's not necessarily going to work out to be something I can do. And sometimes we should go, that might be the lesson. It may not. All right. But what you should get used to doing is going, I don't know how this is going to work out. I'm going to do the first couple of steps to see what happens. Okay. Huge fan of do a couple of steps, see if I haven't broken it. Okay. Because I'm really good at breaking stuff. Really good at breaking stuff. So let's just take this first one, 9x squared y to the 4 minus 2x on y squared is equal to 0. first thing I'm going to do is I'm going to rearrange 9x squared y to the 4 is equal to 2x y squared. Okay, sure. Now, put all the y's one side, put all the x's the other side. So I'm going to have y squared times y to the 4 is equal to 2x on 9x squared. Maybe I cancel that. And maybe this is going to say y to the 6 is to 2 on 9x, 2 on 9x. That x should be there, peoples. All right. Okay. That's kind of interesting. Maybe I could do y is equal to like the 6th root of 2 on 9x. Maybe, maybe not. Who knows? Just going to point out, this actually describes like a curve of points where that first derivative is equal to 0. All right. So, okay, kind of cool. Kind of. And so let's do the other one. 12x cubed y cubed is equal to minus 2x squared y cubed. All right. Again, same trick. We're going to put, so we're going to have y to the 6th is equal to minus 2x squared on 12x cubed. Sweet. And it's kind of funky. My cube is going to cancel out with that. And this is going to be y to the 6 is equal to like the 6th root of minus 1 on 12x. All right. Now, did I happen to find myself, did I stuff up something? 6. That should be a 6. Yep. Good work. All right. Well done. First test pass. All right. It's definitely me not making mistakes. It's in my brain it was a 6. All right. These look really, really similar. Not the same, but similar. So I wonder if they intersect. Because this is an even power, the thing under it has to be positive. So here x has to be positive, and here x has to be negative. There is no value. Well, actually, that's not true. I can't have x equals 0 for this. If I used x equals 0, would this work? All right. Now, because of the rearranging I've done, can't do that. But if I put x equals 0 in here, all right, we can see that x equals 0 all right. Because if I go back up to what they actually are up here, fairly easy to see that if x is equal to 0, then so this is going to make life difficult for us, and I'm going to, at some point in time, I'm going to go, hey, this was a great idea, but I'm going to let it go now because we can find critical points, but because we've got a whole line of critical points, no, I don't want to do that. I'm going to go, hey, let's try, rest assured that if your lecturer actually gives you a question like this, they will check these details and make sure that we're not about to do something you can't do. Me, on the other hand, make it up as I go along. All right. So I'm going to go, let it go. So normally we would go through the classify the critical points, right? Do the Hessian thing. Did you call it the Hessian? Sweet, good. Sometimes they do, sometimes they don't. Some lecturers are funny about it. All right. So I'm going to try a different one. I had a different one. And I'm not sure if that's going to be any better. In fact, actually, I know it's not. All right. Sure. No, that's okay. So let's draw a line to that and go Z is equal to, that's not going to work. Try that. ln of x, y plus 1. Okay. All right. I feel like we should sketch the domain. Again, first question, what restricts the domain? Thing inside the brackets, things I'm taking natural log of, has got to be greater than 0. So I literally start with that. And then that tells me that x, y is got to be greater than -1. And so y is got to be greater than -1 on x. We should be a bit careful about that. All right. This is a bit of a thing where I go, well, it's not a great idea to say that, is it? What did I just do wrong? All right. So when I divide by a variable in an inequality, I need to be sure that that thing is always positive. Otherwise, I've got to change the direction of my inequality. All right. So I want to be a bit careful about this. So what we're going to do is I'm actually going to graph y is equal to -1 on x, because that's my boundary line. All right. So if I graph, just quickly sketch y is equal. So because it's -1, we're going to have this region here and this region here. All right. Now we start taking points. All right. So if I take a point here, let's call it 1, 1. All right. And I put it back into this. I go, hey, this satisfies this equality. And so I can actually be confident that for all of this region here is going to be in the domain. Okay. In a similar way, if I took sort of the corresponding point, -1, -1, again, all of this region, I can be quietly confident is in that. All right. So if I was to take 1 -1, that will be on the line. So I want to be a little bit away from it. So if I took the points 2, -2, all right, a little bit away from it, that makes that -4. So that's not in the domain. If I took a point sort of half, that would be in the point. And so this region here is also in the domain. All right. And so hopefully, if I take the point -1/2, again, makes that negative, but less than 1. So so it's this region as well. So this has kind of got a funky little region where it's kind of doing a thing. Yeah? Sure? Loving the plan. Okay. Right. So let's just do the gradient and see what happens. So if I do, so we're going to do grad of ln of x, y plus 1. And that should be equal to, all right. So it's like because of the natural log, I can go 1 on 1 that. All right. Oh, didn't do a thing. Derivative of the thing inside the brackets with respect to x is just y. In a similar way, this is x on xy plus 1. I should actually go back to the domain bit. One of the things we should do is points on that line are not actually included. So this should actually, ideally, we should sort of do something to sort of indicate in the diagram that the line itself is not actually included. Whether you do that as a dotted line or whether you just make a comment next to it. You know, something like not. Yep. Oh, yeah, no, 2 seconds. Deep breath. Oh, hey, what happened? Hey, what happened? Oh, mood lighting. Yay, good work, Clippers. Sure, well, we got that bit back. Let's do that on that. Right, sure. I feel like they might need to work on the lights in this place. But anyway. All right. So yeah, when we're doing the domain, we should check the boundary. So when we have something like that where there is a definite boundary, we need to check the boundary. Okay, beautiful. Okie dokie doke. Now, I feel like let's call this g of xy. Sorry, we're going to go g of xy is equal to ln of xy plus 1. Then gx is equal to y on xy plus 1. And gy is equal to x on xy plus 1. So if I go gx equals 0, that tells me y is equal to 0. And if I go gy equals 0, that tells me x is equal to 0. All right, sweet. So we have a critical point. All right, so if we're going to do critical points, all right, critical point, then we can do, to classify our critical point, we're going to find the second derivative. So gxx, because this is going to be like y times by xy plus 1 to the minus 2 times by minus 1 times by the derivative of the thing inside the brackets, which is just y. So I'm going to write that as minus y squared on xy plus 1 squared. And gxy is equal to, so if I differentiate this with respect to y, I have to use quotient rule because there's y in both numerator and denominator. And so the derivative of the top line is 1 times the denominator, xy plus 1, minus top line times by the derivative of the denominator, differentiating with respect to y is just going to get me x. On bottom line squared. xy plus 1 whole squared. That needs some simplification. So that's going to be like xy plus 1 minus xy. Simplify that and write it nicely. Okay. That's cool. And so g of y. So differentiate this with respect to y. Again, this is like a chain rule thing because the x is a constant. It's like x, so top line, x, y plus 1. So that's to the -1. So -2 times by -1 times by thing inside the brackets. So minus x squared on xy plus 1 all squared. Okie dokie doke. All right. So my Hessian at 0, 0 is going to be, when I put in 0, 0 into here, I get 0. And this one gets me 0. When I put 0, 0 in here, I get 1. Thank you. And so when I do the determinant, hey, what is the Hessian having a determinant of -1? Tell me. Saddle point. All right. Sweet. Well, that's very exciting. I feel like this is probably a real proper saddle, because even with the domain, it kind of got that sort of saddle vibes, don't you think? And 0, 0 is like is quite literally a saddle point. Maybe not. Um, anyway, so I feel like that's a good way of sort of going, hey, that's where that's what the sort of thing. And I feel like the reason I actually decided to do that example is that's a really good indication of the complexity of the question you might be asked in an exam. All right. So with that first one, when it came to doing like directional derivative, that's a reasonable level of complexity. They wouldn't have gone down the path with something like that where they had horrible little things where it's not obvious what's happening. They wouldn't have gone down the path of asking you what about critical values, tangent planes, whatever. This one, because there is a critical value, it's nice, it's reasonably simple, and it gets you to demonstrate you know what to do. They would do. But even when I looked at it, I thought, oh, okay, I'm not entirely sure what's going to happen, but I have my feelings. So I thought it actually works out to be quite a good example of what's happening. All right. You could also get asked to do with something like this to sketch some level curves, but that's going to be, I know. So if I did like, so if I took my function, so if I had ln, let's do it. I forgot to do this. If I made it equal to e, no, if I make it equal to 1, oh, hey, what's a good number? No, 2, no, because it's ln of x, y plus 1. If I make it equal to, doesn't really matter, so I'm going to say 2. All right, some number. Then what this is going to be, that's equivalent to finding x, y plus 1 is equal to e squared. All right, e squared, arbitrary number. And so this is x, y is equal to e squared minus 1. So y is equal to e squared minus 1 on x. This is positive. So now when I look at it, do my little sketch, it's going to be these bits through here. All right. And putting that in context, your domain is sort of inside here. So that's all in the domain. And so my level curves. And by implication, all my level curves are going to be sort of in that same sort of, they're all going to look very much the same. And that's what's going to, and Eventually, when they get to this, they will become the actual lines and then come through here. So it really does give you like a saddle point. And you've got to, anyway. All right, very excited. Some people look less excited than I feel like you'll, actually, it would be, I wonder if, oh, yeah, no, we'll give it a go. I'm going to just try and see if I can make, we're going to go and pick on something. Come on. All right, let's go here. Let's go that. So if I go there, and if I just go ln x times y plus 1, Wolfram spits out a lot of stuff. See that? It actually spits out a nice little graph of this thing. I don't know that we can play with it. I wonder if it's going to do another one. No. I wonder if I can. So you can see, like I say, it really is giving you sort of something that looks like a saddle. Except for along that edge, it really drops right off. Anyway, goes right down to minus infinity. It's kind of cool. And eventually it goes up to plus or minus infinity, but it goes going up to, because it's a natural log, it goes very, very slowly. Very, very slowly, peoples. All right, cool. I think that's kind of fun. I'm happy about that. Okay, let's go back to, what we're going to do is I'm going to actually swap that for a bit so I can point at this so it's on the recording so people can see what I'm doing. So I'm just going to go back up to the top. All I did when I did this, go to Wolfram Alpha, wolframalpha.com, typed in the function, it just showed up a thing where it did this. You'll notice it's also told me what the domain is. All right, so Wolfram Alpha is really useful in telling me what's going on. Ooh, check it, series expansion. All right, blah, 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 lots of other things. It tried to integrate it for me. Does all sorts, it sort of kind of tries to guess what you wanted it to do. So it can be quite fun to do. And it will throw up, you can, like, if you want to differentiate something, you can throw it in there, integrate. And if you read the pages, you can actually work out how to do more complicated things with it. So yes, for solving mathematical problems, if you know what the problem is, Wolfram Alpha, pro strat. All right. ChatGPT, terrible plan. Terrible plan. Cannot emphasize how terrible a plan. All right. Okay. So, all right. I meant to grab this and go. What's the time? So, I feel like that's. Does anyone have any more questions about multivariable functions and things we might do with them? That's covered all the major things you'd do in the exam. All right. All right. Anything else people want to go? Like the next thing on the list is diagonalisation. All right. Everybody love diagonal. You want to skip diagonalisation? Like there is a diagonalisation pros and cons. Actually, oh, do I have it? Yes, I do. So one of the tutors was where'd it go? That'll do. He showed me the question that says if I do A, it said find A by 0, 0, 1. This is not what the question actually said, but it's equivalent. And A by 1. Oh no, it said that's equal to 5. And a by 1, 1, 0 is equal to, I should have said 5, 5, 0. All right. And what was the last one? All right. Find the matrix P that diagonalizes. Okay, sure. So, what are we thinking? So, because we are told a by 0, 0, 1 is equal to 5 by 0, 0, 1, lambda is equal to 5, vector 1, lambda 1, we'll call it lambda 1, and that is equal to 0, 0, 1. It is literally this is telling you the eigenvectors and the eigenvalues, all right? So quite often in maths exams, we won't ask you to do horrible things. We will go, hey, what are these things, all right? Because we can, all right? So, and so this one, so we're going lambda 2 is equal to 5 and v2 is equal to 1, 1, 0. And lambda 3 is equal to -1 and v3 is equal to 1, -1, 0. Okay. So my P would be equal to 0, 0, 1, 1, 1, 0, and 1, -1, 0. Okay, sure. And the associated D is just going to be, because I put the two eigenvectors with eigenvalue of 5 first, it will look like that. Okay. So what we've done is we've said, actually, I recognize the information you've given me is telling me eigenvectors and eigenvalues, and I can just state what my P is from that. All right. So I actually kind of gone, you know what? I could have done a slightly different thing. All right. It's kind of slightly different. We'll see how we go. Now, no, we'll let it go like this. When I come to for me to be able to go, hey, we did what is it? P inverse A P is equal to D. Sound like a thing? Is that the right way around? Given my ability to write things the wrong way around, I'm going to go, yep, all right. A lot of people nodding. We're going to assume that I've got that the right way around. Sure. And so I've got my P. If I had my P inverse, I could actually work out what I could work out. I could work out what A is. And so I could go, because A would be equal to P D P inverse, wouldn't it? Yeah. Nod wisely and say yes. Yes, Nick, I do believe you. All right. Unfortunately, I don't have P inverse. But if I do 0, 1, 1, 0, 1, -1, 1, 0, 0, and 1, 0, 0, 0, 1, 0, we're trying to make this quick. So you guys are 1B, you can do row operations. They won't get you to do this in the exam. Yeah, no, I won't do that. All right, I'm going to swap row 1 and row 3. So 1, 0, 0, 0, 1, 0, 0, -1, -2. So we did row 3 is equal to row 3. Take row 2. So row 3, take row 2. Divide through by -2 on row 3. So 1, 0, 0, 0, 0, 1, 0, 1, -1, 0, 1, 0, 0, 0, 1, minus a half, plus a half, 0. And then we're going to go one last step, 1, 0, 0, 0, 1, 0, 0, 0, 1. We did row 2 is equal to row 2 plus row 3. And so this is going to be minus a half. This is going to be 3 on 2. Got my 0, got my 0, got my half, got my minus a half, 0 and 0, and a 1, forgot that. So I could do this. This is going to be tedious. Do we want to do it? Sure, what the hell. We will try and do it. I am going to try and do it quickly. So I need to be a little bit further down, don't I? So you can see what I'm doing. We'll see what I have done. All right. So my A should be equal to, I said P. So that should be, what did I say? 0, 1, 1, 0, 1, minus 1, 1, 0, 0 times by D, 5, 0, 0, 0, 5, 0, 0, 0, -1. I did write -1. Beautiful. And then this thing, 0, 0, 1, minus a half, 3 on 2, 0, minus a half, 0. All right, let's do the fun part at the start here. So let's just do this product first. And so we're going to go 0, 0, 0, 0. Hang on, that way. Across the row, down the column. 0, man, that's going to be 5. -1. Yep. And that one's going to get me 5, 0, 0. Can't really get me 0. Pause momentarily. I go that times that. No, that should be 1. Oh, that should be a 1. All right, sweet. That should be a 1. And then 0, 0, 1, minus a half. 3 on 2, 0, -1 on 2, 1 on 2, 0. Oh, okay, not tedious at all. All right. Those people playing along at home should be ready to go. All right, I'm going to put myself 5 at the top of this. And we're going to go 1B, 0. So -5 on 2, +1 on 2, 5 on 2, so -5 on 2. So -2, -5 on 2, +1 on 2, -4 on 2, -2. This one, 5 on 2, that's a 2. 5 on, yeah, okay, sure. Yep. 0, 0, 0, that's a 0. 0, -5 on 2, that's a 3. Is that right? That one. Okay. -5 on 2, -6 on 2, 3, sure. 0, fucked up. Pause. That's like 15 on 2. Made a mistake. You people, what are you doing? You people going too fast, way? Missed it. All right, let's do this again. 0, so that's like 15 on 2 plus that 16 on 2. That should be an 8. which means I got this number wrong. Let's go back. That should have been 15 on 2 minus, that should have been 4. That should have been a 7. That should have been a 7. All right. Relying on you people to stop me making stupid mistakes. I mean, I realize that's asking a bit much of most people. 5. All right. Sweet. I can do that. All right. Hashtag, this is not something they would get you to do in an exam because that is too tedious. Yes. What's that? What's that? The 3, did I do that one wrong? So that one should be second row, first column. Yeah, minus, yes. Yes, that is what I want to hear. Oh, yeah, that's yeah, it's all right. One of the lecturers when I first started sort of politely pointed out that your IQ drops by about 20 points when you sit in front of a lecture. Um, making mistakes while you're doing stuff live is kind of par for the course. So this whole I gave you eigenvalues and we expected you to diagonalize, that is a thing. That is definitely a thing. And so it kind of demonstrates the information from a different perspective. All right. So now I could say more about this, but there's some people who seem to think that this was a bit boring and I don't want to do it. Do we have other things you would like me to talk about? Okay. Where did I put my page with notes? Okay. Okay. Typically, we don't do rotation matrices in 3 dimensions because it's just unpleasant. All right. So linear transformations. So linear transformations has this property that like f of a constant times by the vector is just the constant times f of the vector. All right. And f of one vector plus another vector is equal to f of vector plus f of other vector. All right. Now, hard to see why they shorten that to LT. It's just being lazy. So we know if we go f of x is equal to a times x, then a, the standard matrix, is going to be f of, let me use a, I'm not sure if you've seen this notation. What do they call standard? I think it's the phrase is all right. So we use E1 to En to be quote standard basis, which is 1 0 0 0 1 0 whatever. All right. where actually the number on the subscript tells you the position where the 1 is, and every other value is 0. All right. Should be something you're familiar with the idea of. All right. So if we're doing a rotation, all right, so let's draw ourselves a picture. If in doubt, draw a picture. We should, what? Picture. All right, we should have some axes, and then we should have a unit circle. That looks remarkably circular for a unit circle for me. So we're pretty happy with that. Now, typically, we treat a linear, like a rotation, as an anti-clockwise rotation through theta degrees. All right. So if I go, this angle here is theta. This point here, we know is going to be cosine of theta, sine of theta. Yep. We're all happy with that. We love our unit circle. All right. So my standard matrix A should be my transformation of 1, 0 and my transformation of 0, 1. Right? Trust me, there are things that do all the time, and we should go, yep, all right, sure. So if I take this point here and rotate it through theta degrees, that is that point. All right, so my A, that maybe what we'll do is we'll go f of 1, 0 is literally just going to be cosine of theta, sine of theta. Cosine of theta, sine of theta. All right. So when we come to other point, where is it? Nope, nope. Kind of a little bit more difficult. So maybe what I could do is I could go, hey, this bit here, what would that angle be? That's like, so it's like pi on 2 minus theta. Or actually, this should be like cosine of pi on 2 plus theta, and sine of pi on 2 plus theta. Oh man, that's a bit unfortunate. Anyone happen to remember things off the top of my head? All right, sure. We kind of know what it is, but I kind of don't want to go, hey, I know it's this. All right. So I'm going to digress a little bit into stuff we did in 1M. Right. So if I consider cosine of pi on 2 plus theta, all right. Cosine is, so it's going to be cosine of pi on 2 times by cosine of theta minus sine of pi on 2 sine of theta. Cosine of pi on 2 is, all right. Maybe I should have written in the whole formula. No, you guys are good. Sine, I'm going to put it in here. Sine of A plus B is equal to sine A cos B plus sine B cos A. While we're doing this, cos of A plus B cos A cos B minus sine A sine B. All right. So sine of pi on 2 plus theta is equal to sine of pi on 2 cosine of theta plus sine of theta cosine of pi on 2. All right. So sine is 1 cosine of theta plus sine of theta times 0. All right. Slight digression, but this means that this should be minus sine of theta cosine of theta. So I can derive this quite simply from knowing how to calculate the standard matrix. All right. And so tedious, a little bit tedious, but I can make it happen if I want to. Oh, you know what? Oh, could I show could I show that a rotation is a linear transformation? So think about this. I can do this, people. All right. So K should make no difference. No, no. So if I have f of x as a vector is equal to a times x, where a is equal to cos theta minus sine theta. Okay, what do I have to show? I have to show that f of a constant times by x is equal to constant times f of x. All right, sure. That's a bit difficult, isn't it? So maybe I'm going to do, so if I consider x to be just a vector x, y, this is where I go, every so often I have these ideas and I'm not sure how it's going to work out. So a times x is going to be cos theta sine theta. Tedious. Um, all right. If I do a times kx, that should be the same thing. It should be like kx cosine theta minus ky sine theta, kx sine theta, and ky cosine theta. And so therefore a times kx is going to be equal to, I should point out that I can take the k out here. X cosine of theta. I'm going to go dot, dot, dot. You guys can fill that in because that's getting boring. we kind of know that's going to be true. One of the things we don't know, no, that's not going to be very fun. They won't bother doing that. Doing things like showing these things is just doing that, and it's not really worth doing. I feel like I'm not going to bother doing completing that because it's just not going to work. Just not going to do anything that's remotely interesting. Okay. So, where were we up to? Where was I up to? But that. Six. Okay, so that's not useful. What will they do with linear transformations? I don't know. Linear transformations, show that it is a linear transformation. Show that no. So the domain and range. Kernel. So you guys talk about the kernel, don't you? All right. What is the kernel? Kernel of a linear transformation is the null space of the standard matrix. So we should be, this is one of those things where I'm a little bit like, no, you're fine. When you're talking about a linear transformation, people treat the null space of the standard matrix as the same as. They're equal to, but they're not the same as. Null space of the standard matrix and the kernel of the linear transformation. Null space applies to a matrix, kernel applies to a linear transformation. And so the reason I go on about this is what we're doing is we're teaching you to talk about these things, right? All right. And so it's like when your international friend says, look at all those sheeps. You kind of go, oh, no, that's not what we say, right? It's one of those things. We don't talk about the null space of a linear transformation because it's a kernel, all right? And so it's kind of not a big deal. You know what people are doing, but it's about about demonstrating complete understanding of what the things are, all right? So being a little bit pedantic. It's like studying grammar, but for mathematics, okay? And really, maths is a language, and we want to study the grammar a little bit, okay? I never thought I'd be a grammar Nazi, and I'm really not. But also, we want to be a little bit, this is what this thing is. All right. Can I think of a nice linear transformation off the top of my head that's going to go somewhere nice? So, all right. So we're going to just put that line down, right, though? Okay. So that's one thing we can do. If we're given a linear transformation, I'm trying to think of a linear transformation that is non-trivial. Oh, do I have anything here? Let's go. No, not that one. That one. Do we have? It would have been. Wrong one. Would it would have been that one, Nick? Practice questions. Come on. See how we're going. No. Eigenvalues. Microprocess. No. Too far. We did workshop. Linear transformations after eigenvalues or before? Before. Workshop. Come on. Let's see if we got something that looks like fun. Oh, we could do that, but no, we don't want to do that. Oh, really? Written. No. Oh, okay. Okay. And maybe what we can do is just something like no, that's just going to make the z go to 0. Sure. Yeah. Oh, the problem is I don't want to do something too trivial, but I don't want to do something too complicated. And moving away from trivial is fraught with danger. It's a very slippery slope. All right. What the hell? How bad can it go? Have you ever thought about all right. If I project onto a subspace, a plane that goes through 0, it will be a linear transformation, won't it? Nod wisely and say yes. Yes. Ideally, what I do is I get an orthonormal basis for this space, right? Because I'm doing a projection, right? So if I go the vector 1, -1, 0, if I call that like V1. Oh, poo, sorry. I need to click on that thing. Sweet. All right. So if I project onto that thing. So now, what I want to do is I want to pick an orthogonal vector. All right. I don't want to have to do the orthogonalization. I don't want to do the Gram-Schmidt process. All right. And so if I pick a vector, so if I pick my V2 such that the dot product is equal to 0, so 1, 1, because of the 0 here, because of that 0 at the end, I can just choose the appropriate value. I just pick the value that makes this vector on the plane, in the plane. And so if I go 1, 1, then Z has to be 2. And those two vectors are mutually perpendicular. All right. And so then I normalize 1 on root 2 by 1 -1, 0. And 1 on root 6 by 1, 1, and 2. Sweet. Oh, too far. I must have, when I got here, I had the document camera and the computer set up so that I could push it right up against the computer, but I must have inadvertently pushed the computer forward. Anyway, so I'm going to find my standard matrix. All right, my A, which is going to be f of 1, 0, 0, f of 0, 1, 0, and f of 0, 0, 1. Okay. And f of 1, 0, 0 will be equal to 1, 0, 0 dot with 1 on root 2, 1 -1, 0, times by 1 on root 2, 1 minus 1, 0, plus 1, 0, 0, 1 on root 6, 1, 1, 2, 1 on root 6, 1, 1, 2. All right, the reason I've done this is these two things, they're constant and they can come out the front. And so I can go 1 on 2. My dot product, so the dot product of this vector is simply going to be 1, and so I'm going to times by 1 minus 1, 0, plus, same thing, 1 on 6, dot product is equal to 1, and so 1, 1, 2. This is going to be a half minus a half, 0, plus 1 on 6, minus 1 on 6, 1 on 3. Let's add those up, and so that should be 2 on 3. That should be minus 2 on 3, and 1 on 3. Sure. One column. Everybody love that. F of 0, 1, 0 is equal to, let's call this V1 and this V2. And so I'm going to go 1, 0, 0 dot V1 times by V1 plus 0, 1, 0, 1, 0 dot V2, V2. All right, so this is going to get me a half. The dot product is going to be minus 1 for that one. And then we're times by 1 minus 1, 0. And that one is going to be plus 1 on 6 times by 1 times by 1, 1, 2. Nobody is loving that. And so we're getting like minus a half, 0, plus 1 on 6, 1 on 6. That should have been a plus, and so that should be 1. I really do like it when I get these things right the first time. But, so that's 1 on 3, and that's 2 on 3, and that's 1 on 3. Sweet. Minus. Sweet. All right. F of 0, 0, 1. Conveniently, when I go 0, 0, 1, dot V1, V1, plus 0, 0, 1 dot V2, V2 is equal to, this dot product is 0 plus 1 on 6 times by 2 times by 1, 1, 2. And so this is going to be equal to 1 on 3, 1 on 3, 2 on 3. All right, so my A is equal to, let's do this, push this up a little bit, do the thing. A is going to be 2 on 3, minus 1 on 3, 1 on 3, minus 1 on 3, 2 on 3, 1 on 3, and 1 on 3, 1 on 3, 2 on 3. Sweet. Everybody love that. Okay. Anyone want to tell me what the kernel is? All right. So one of the joys of projecting onto a plane is the dodgiest thing, right? If I was to take the normal vector for that plane, that's going to be the kernel of this linear transformation. Now, all right, so I could go through, all right, I could write this as like 1 on 3 by 2 minus 1, 1, minus 1, 2, 1, 1, 1, 2. All right. I could do the row reductions on that and go, hey, what is this thing here? Or the normal for that plane is going to be 1, 1, minus 1. You reckon? Yeah, no, maybe. So my claim is if I do A times by N, that should be equal to 0. I have my feelings about this because I may have stuffed up, but hey, I'm prepared to give it a go. 2 minus 1, 1, minus 1, 2, 1, 1, 1, 2, times by 1, 1, minus 1, minus 1. Going to put my 1 on the 3 out the front. And so this is going to be 2 minus 1 minus 1. Ooh, that's a good sign. Minus 1 plus 2 minus 1. 1 plus 1 minus 2. All right. So now, how can I justify that this is the kernel without doing any more calculation? Let's think. So, rank theorem. What does my rank theorem tell me? All right. What does my rank theorem tell me? It says dimension of the range plus dimension of the kernel is equal to, they usually say n, the dimension of the domain space. I know this number is 3. I'm projecting onto a plane which I've given an orthonormal basis with 2 vectors in it. So this must be 2. So this thing has to be 1. So the dimension of the kernel has to be equal to 1. I've given a vector in the kernel, and if it's dimension 1, then that forms a basis for the kernel. Do we love that plan? All right. So sometimes we can take these other ideas. All right. So we can take other information. I know I'm projecting onto a plane. I know how to read off the normal for that plane. All right. I know how to read off the normal. That's all I've done. I've just gone, x plus y minus z. The normal is 1, 1, minus 1. I've demonstrated, I actually went to the trouble of demonstrating that it must be in the kernel. All right. Transformation of that vector is equal to 0, must be in the kernel. All right. Argued why the dimension of the kernel must be equal to 1. This thing forms a basis for my kernel because I know the kernel is a subspace. Do we love the plan? All right. You are allowed to do things like that in the exam. All right. There is absolutely nothing wrong with doing a trick like that. Okay. In fact, the marker will look at it and go, slick. That is, they will pause, right? They will pause. So when I first started marking, if I got an answer like that, I would have gone to the coordinator and go, I think that's awesome. Can I give it 4 marks? And they will go, yeah, sure. It'll be fine. All right. So you can be a little bit creative. All right. So I'm actually going to go to the trouble of saying the people who mark the exams are not the same as the people who mark the assignments. So tutors do a lot of marking of the assignments. Lecturers do mark the exam. So there were some tutors who were considered good enough to mark exams. All right. And that is because they were like me and they'll go, I think that's really cool. Am I allowed to give that 4 marks? Right. So if there was something I wasn't sure about, I would check with them. So you can definitely do that. There is, as far as I see it, nothing wrong with doing that. Okay. All right. I think that's like that's sort of with linear transformation, something where you show it's a linear transformation, finding the standard matrix, using the rank theorem for something, finding the basis for the kernel or the range, kernel or the range. All of those things are things we could do, and combinations of those things. You know, if I'm finding a basis for the kernel, then I might want to go, so what must be the dimension of the range? And so that's using your rank theorem. All right. So combining those things in some way are the sort of things that ask about linear transformations. Okay. How are we feeling? Do we have more things we'd like me to talk about? All right. Anyone? All right. I'm going to wait momentarily so that the people in the Zoom can put up a question if they want. Oh, hey, there we go. Speak of the devil. Phase lines. Oh, phase lines. Fucking phase lines. Sure, phase lines. Where's my piece? Where did that go? I want that. Okay. Um, so I'm going to get rid of this bit for a second. Okay. So phase lines really only apply when I've got dy and dx is a function of y. Okay. And so um, I'm trying to think of a nice y that I could do. Oh yeah, yep. Oh, I know what it is. Yeah, yeah. I'm going to do that. All right. Now, so what we do is we want to find y such that f of y equals 0. Sound like a thing? And so that would be y plus 2 equals 0, and ln of y squared plus a half equals 0. All right. This is y is equal to minus 2. This one here, that would be the same as saying y squared plus a half is equal to 1. And so y squared is equal to a half. And so y is equal to plus or minus 1 on root 2. Okay, so I've got 3 phase lines. Now I'm going to do something a little bit different. I'm going to do this like this is x and this is y. This literally says y is equal to minus 2. Y is equal to minus 1 on root 2. Y is equal to, all right, sound like a thing. Now, normally what you do with your phase lines is you would go minus 2, minus 1 on root 2, 1 on root 2, right? But when we think about this, this is telling me about the derivative, about the value of the derivative. I've worked out where the derivative is equal to 0. On these lines, if I start on these lines, do you know where I go? Think about if you're doing Euler's method, right? If I'm on this line, the derivative is 0. So I take a step with the derivative of 0. And then I keep on taking more steps with derivative of 0 because the derivative is always 0 along that line. But, sorry? Yep, that's it. No, deep breath. Yeah, there we go. And so if I start at 0, if my derivative starts at 0, because the thing is only dependent on the y value, if my derivative starts at 0, it doesn't get the option to change. And so phase lines are horizontal lines, which if I happen to be on, I stay on. And so I can either go towards my phase lines or away from my phase lines. There's the thing. I had a pen. Don't know what happened to the pen I had. Sure, we're using that one now. I'm just not going that far. Sure. Okay, so let's take y is equal to 0, for example. So if I go f of 0, that would be 2 times ln of a half. And ln of half is minus 2, so this is a negative number. This is negative in this thing. That means my derivative is negative. All right, derivative is negative. My function decreases. So my function is going to do anything starting in here is going to come down. So the thing they might ask you would be, if y naught is equal to 0, find limit x goes to infinity f of x. Sorry, I should say y of x. All right. And that's saying, actually, I'm going to go towards this phase line. All right. And so this, I can go, well, because this was minus 1 on root 2, this is equal to minus 1 on root 2. So you saw that question in one of the assignments or the Mobiuses or whatever. In fact, I think you saw it in both. But it's the sort of thinking we do. So if I go through a similar process of going, well, I'm going to do, say, f of 1. All right. And so that's going to be equal to like 3 times ln of 1.5. 3 on 2. ln of 1.5, positive. That thing is greater than 0. And so in this region here, the thing is positive. Oh, hey, there it is. Where did that happen? Genius, I tell you. And so my function is increasing in here. So and because it's increasing, it's going to curve upwards. All right. Similarly, if I do f of minus 1, again, that's going to be 1 ln of 1 ln and so if that's 1, that is going to be that's going to be 3 on 2. That is also positive. So that's saying that I'm increasing that region. But again, because I'm constrained above, it approaches that line. All right. And since crossing phase lines tends to change, so we've got to be a bit careful. We shouldn't just go, it should be some negative value. That should be minus 1 ln. If I put in 3 minus 3, that'd be 9. That'd be like 9.5. That again, so that's less than 0. So again, that's decreasing. So thinking about this from the point of view of what's actually happening to the graph, what's happening to the solution of this differential equation, all right, we can work out this thing. But we can draw the traditional phase line diagram like they taught you in lectures, because you can go, hey, that goes that way, that goes that way, and that goes that way. And so you can see, what do they call them? What are the terms? What's the fancy terms for phase lines? It's like attractive, no, convert, no. What a That's the word. Mhm. -1 on root 2. Unstable. Y is equal to -2 and 1 on root 2. Okay, so this is the phase line diagram that you've been taught to do in lectures. I prefer to think about it as what you would draw the solution for the differential equation. All right, because that allows you to see that sort of is more intuitive, because what you were being told about is the value of the derivative, but we're really doing a sign diagram for the derivative. Okay, how do we feel about that? Sweet. Have we had enough of me talking? Anything else, anyone? All right, so one of the other things to say is my fancy little picture here, all right, that may not be what the lecturer is sort of asking you for, but it is not wrong. All right. See, I've labeled my axes. I've been clear about what I'm drawing. It is not wrong, and it can help you understand what is happening. Okay. So doing something that helps you understand is not a bad thing for the exam. Like if I see this, but then I see you've written down the wrong numbers, I will be a bit torn between going, well, you've demonstrated you understand what you're doing, but you've written the wrong thing, right? And so, but I have something on which to base giving you a mark for, even though you've written the wrong answer. Okay. So it allows me to go, that's good enough. I'm going to give you the marks. Okay. So things that support your answer are always good. All right. As someone who's marked a lot of exams, I will know if you don't know what you're doing. All right. I've seen people try and bluff, and I'm prepared to say I'm 95% certain that every time someone tried to bluff, I noticed, right? So I can't be 100% sure because I can't know what they were thinking, but also it's fairly evident in what you do. Things like not writing much make it seem like you don't know what you're doing. If you write down the things that you thought that, like, I saw this, therefore I know this, that tells me that you know what you're doing, right? If you don't write stuff, what you're saying is, I'm not really sure why I think this is the answer, but I think this is the answer, right? If you just write down the answer, leaves the person marking it with the feeling you didn't really know what you were doing. So if you go away with nothing else, write down the things you are seeing. If you are stuck on a problem, write down the things you are seeing, and write down what that will tell you, what that next thing it is it tells you. Because if you just write, I see this, that means this, don't know how that helps me, then the marker will go, yeah, actually, that's one of the things we wanted you to know, so I can give you a mark for it. All right. So it is just a good strategy. All right. Have we had enough of me talking? I feel like that's a yes. Thank you for your attention. Thanks for coming along. This stuff will go up eventually. and yeah, it'll be available. There is a whole lot of other revision seminars that have been done by either me or David Butler. I'm going to do the stop sharing for a second. So you can, oh, hey, there's an extra person. And right, sure. So you can look on our website for more. They have the notes that we've done and the video link as well. Good luck with the exam. Remember, Math Learning Centre is open until, well, so we're actually open all the way until till the end of the year, basically. But from the beginning of the exams, we go to doing 1 till 4, because nobody will be coming and asking me questions in a day or two's time. They will all give up and go on, yeah, no, you don't need to talk, you don't need to ask questions in a second. So do ask questions, but good luck. My numbers are all out. No worries, you're welcome. Oh, hey, no, got a mix up. Boo. That is why I write what's even on the top of it. Thank you guys. All right. Okay, I'm going to stop the recording. I should have stopped the recording a little while ago.